Welcome to this presentation on Group 7, the halogens. Group 7 elements are known as the halogens. They are reactive nonmetals found in the P block of the periodic table. The main halogens studied are fluorine, chlorine, bromine, iodine, and astatine. Specification overview and learning objectives, position in the periodic table and electronic structure. The halogens are located in Group 17 of the periodic table. They all have 7 electrons in their outer shell, which gives them similar chemical properties. The halogens are found in Group 7, Group 17 using epoch numbering, on the right-hand side of the periodic table, just before the noble gases. All halogen atoms have 7 electrons in their outer shell, giving them similar chemical properties and explaining why they are grouped together. For example, fluorine has the electronic configuration 1s squared 2s squared 2p, while chlorine is 1s squared 2s squared 2p 3s squared 3p. This outer shell structure means halogens tend to gain 1 electron in reactions, forming halide ions with a -1 charge. Down the group, the number of occupied electron shells increases, leading to larger atomic radii. This increase in size has a significant effect on properties such as electronegativity, bond strength, and oxidizing power. The high electronegativity of halogens, particularly fluorine, explains their strong tendency to attract electrons and form ionic compounds with metals. The periodic position of halogens also explains why they are nonmetals and why they often exist as diatomic molecules, such as Cl and Br, joined by a covalent bond. Physical properties, color, state, and volatility, trends in melting and boiling points explained. Fluorine is a pale yellow gas, chlorine is a green gas, bromine is a red-brown liquid, and iodine is a dark gray solid that forms a purple vapor when heated. This progressive change in color intensity down the group is due to changes in how the halogen molecules absorb visible light, which in turn depends on molecular size and electron arrangement. At room temperature, the state changes from gas to liquid to solid as you move down the group, indicating increasing melting and boiling points. These trends occur because larger halogen molecules have more electrons, leading to stronger London dispersion forces between molecules. As a result, more energy is required to separate the molecules during melting or boiling. Volatility decreases down the group, meaning iodine evaporates much less readily than chlorine. Halogens exist as simple molecular substances, meaning that within each molecule the atoms are held together by strong covalent bonds, but between molecules the attractions are much weaker London dispersion forces. As you move from fluorine to iodine, the number of electrons in each molecule increases, leading to greater temporary dipoles and stronger dispersion forces. Consequently, more thermal energy is required to overcome these forces, resulting in higher melting and boiling points. For example, chlorine boils at -34 degrees Celsius, bromine at 59 degrees Celsius, and iodine at 184 degrees Celsius. Importantly, the strength of the covalent bond within the molecule does not significantly affect boiling point, as boiling involves separating molecules, not breaking covalent bonds. Oxidizing power and reactivity trends, reactions with metals, formation of halides. The halogens are strong oxidizing agents, meaning they readily gain electrons in chemical reactions. However, their oxidizing power decreases down Group 7. Fluorine is the strongest oxidizing agent, while iodine is the weakest. This trend can be explained by considering atomic radius, nuclear attraction, and electron shielding. Down the group, the outer shell electrons are further from the nucleus and increasingly shielded by inner shells, making it harder for the atom to attract an extra electron. As a result, the tendency to be reduced decreases. This trend has important consequences for displacement reactions, where a more reactive halogen can displace a less reactive halide ion from solution. Halogens react readily with metals to form ionic metal halides, a reaction type that demonstrates both periodic trends and redox chemistry. In these reactions, the metal atoms lose electrons to form positive ions, while halogen molecules gain electrons to form halide ions. Down the group, the reactions become less vigorous, reflecting the decreasing oxidizing power of the halogens. Fluorine reacts explosively with many metals, while iodine often requires heating to react. These reactions are exothermic, releasing energy as strong ionic lattices are formed. Displacement reactions and halide ion tests, uses of chlorine and environmental considerations. A more reactive halogen can displace a less reactive halide ion from an aqueous solution, providing clear visual evidence of reactivity trends. For example, adding chlorine water to potassium bromide solution results in the formation of orange bromine, indicating that bromide ions have been oxidized. Halide ions are also identified using the silver nitrate test, which requires acidifying the solution with dilute nitric acid before adding silver nitrate. Chloride ions form a white precipitate of silver chloride, bromide ions form a cream precipitate of silver bromide, and iodide ions form a yellow precipitate of silver iodide. Chlorine is the most economically important halogen and is used in water treatment, where chlorine kills harmful bacteria and pathogens, making drinking water safe. This process relies on chlorine's strong oxidizing properties. Chlorine is also used in the manufacture of polychloroethene, commonly known as PVC, which is used in pipes, window frames, and insulation. Additionally, chlorine is involved in the production of bleach and disinfectants. However, there are environmental and health considerations associated with chlorine use. Chlorinated organic compounds can be toxic, and the formation of chlorinated byproducts in water treatment must be carefully controlled. To summarize, Group 7 elements are reactive nonmetals with 7 outer electrons. Reactivity decreases down the group, while melting and boiling points increase due to stronger intermolecular forces. Thank you for watching.